Hello, in this video we're going to be moving on to a new section in the class, which is going to be about some new topics, double integrals and line integrals. And these are both types of integrals that occur when you have functions of more than one variable. We're going to discuss over the next 2 weeks and 7 videos what these two types of integrals are, double integrals and line integrals. So first, in this first video, I'm going to provide an introduction to double integrals and then look at some examples. So in order to introduce double integrals, I first want to briefly remind you about single integrals. And so this is fairly recent that I've just been discussing this in a different video, but still I want to remind you because double integrals are a natural extension of an integral when there's only a single variable. So recall that if we have this definite integral, this represents the yellow area above the x-axis and below the graph of the function f in between the two limits, a and b. And we can compute these single integrals by dividing up this region that we're trying to calculate the area of into smaller regions and then refining the division. So dividing the interval from a to b up into 2 subintervals, 4, then 8, and then 16. And we get better and better approximations, and as the limit, as we use infinitely many subintervals, we get the exact area in between the x-axis and the graph of the function f. And as I discussed last time, the fundamental insight of calculus is that this single integral is related to differentiation by the fundamental theorem of calculus, which I covered in the previous videos. Okay, but what about if we have a function of 2 variables? So in the single integral, we just have a function f of 1 variable. But if we have a function of 2 variables, then the graph, rather than being a single line, will be a surface. And I discussed this when I introduced partial derivatives, how the graph of a function of 2 variables is a surface. And so we want to consider something like the area in between the graph and the x-axis. When we have 2 variables, this will become a volume underneath the surface and above the xy plane. And so a double integral is computing this volume, or we can think of it as representing this volume. So if we have a function, as I discussed when we were talking about partial derivatives, the graph z equals function f of 2 variables x and y is this surface shown at the top of this region. And then the double integral over a rectangle R at the base of the region is going to be the volume above R. So R is the region in the xy plane that I'm tracing out here, and below the graph of the function f. So this is the natural extension of a single integral representing the area. The double integral represents this volume. And you can define the double integral in a similar way to the single integral, where we divided up the interval from a to b into small pieces and then approximated the area by rectangles. In the case of a double integral, we divide up the region at the base, so the region we're integrating over, which is R in this case, is a rectangle, as shown in the picture. We divide it up into small rectangles with area delta A, and we approximate the volume by these cuboids. One example here is shown in yellow, but we would fill up this entire volume by approximating it with cuboids. And then we take the limit as this delta A goes to 0, as it gets very small. And in that limit, we get the double integral. Okay, so this is the definition of the double integral. Of course, dividing up the region into these small boxes and then approximating the volume by cuboids is not a very practical way to compute the volume. It might be something you could do in some cases. But we want to know, is there something similar to the fundamental theorem of calculus that we have for integrals when there's only a single variable that we can apply for double integrals? Yeah, so can we calculate this volume using a method similar to the one for the one-dimensional case? So we want to be able to calculate this double integral over a region R. And remember, this would represent the volume above the rectangle R, region R, and below the graph of the function f. How can we calculate this double integral using a method similar to the one-dimensional case? Well, the first question we'll consider is what is this dA that we put here? We call this the area element, and it represents somehow the limit as the delta A, the area of the little rectangles we divide R up into, go to 0, similar to the dx in the case of a single integral. And well, this dA is going to depend on the coordinates we use to describe the region R. And so I've been talking about R being a rectangle, but R could be other types of regions in the xy plane. But let's suppose R is here an ellipse, and suppose we just use the normal xy Cartesian coordinates. Then the area of a small little rectangle that we divide up this region R into is going to be the width times the height. And so if we divide the y-axis up into little regions of length delta y and the x-axis into little intervals of length delta x, then the corresponding delta A is going to, of course, be delta x times delta y. And in the limit, as this area goes to 0, we think of this as dA, this area element in the double integral, is equal to dx times dy. And this tells us how we can evaluate the integral by using this particular Cartesian coordinate system. And so the double integral of over the region R of this function f with respect to the area element dA is equal to this double integral of f dx dy. And what we can do then is we can evaluate the two integrals one at a time, the integral with respect to x first and then the integral with respect to y, as what we call an iterated integral. So how do we evaluate this double integral? We have dx dy. So let's suppose R is a rectangle. This is the simple case, and this is the case that we're mostly going to consider, the simplest case really. And suppose R is a rectangle where x goes between 2 points A and B, and y goes between 2 points C and D. Then this double integral can be converted into an iterated integral where we integrate with respect to x first with y fixed, and then we integrate with respect to y once we've integrated with respect to x first. And what we're really doing here, if you think about it, when we fix y and do this inside integral, is that we're calculating the area of a slice of the graph of f. And so I'm going to try to draw a picture of what this means. So let's consider these three-dimensional axes. So this is the x-axis, y-axis, z-axis. And this is similar to the diagram I drew when we were discussing partial derivatives. And we have a region is a rectangle in the xy plane. So this is in the xy plane, a region that we're integrating over, R. So this rectangle is the region R. So I've drawn it kind of in perspective here, is why it looks like a parallelogram, but it's a rectangle in the xy plane. And x goes from A to B, y goes from C to D, and then the double integral represents this volume. So let's say we have this graph of f, which is a surface of the xy plane. There will be some function defining the top of this sort of cuboid, but with a curved top. And if we fix y and do the single integral with respect to x for fixed y, say we fix y here, and then we're looking really at the slice of this function. So this slice will be a curve. So when y is fixed and we vary x, we are looking at this slice. And when we do the inside integral in this double integral technique, as shown on the slide, what we're getting is the area of this slice. And the integral, as shown here on the slide, from a to b of x and y. The x is what we get when we fix a given y, and then we integrate x from a to b. We get the area of this slice. And so, what we're really doing when we're doing this iterated integral technique for evaluating the double integral is we're calculating the areas of these slices, and then we integrate up the areas of the slices. Think of that as adding up the areas of all the slices. And this is intuitively why we can evaluate the double integral as these iterated integrals, where we integrate first with respect to x and then y. And so when we do this, we call the integral we do first the inner integral. And we could do first the inner integral and then the outer integral. So you do the inner integral, you get this area of these slices as a function of y, and then you integrate that. And one thing to notice is that it actually doesn't matter which order you do it in. You could also consider y to be the variable in the inner integral. And say, suppose you fix x instead of fixing y, then we would get a slice in this direction. Something like this slice. Try to draw here, which would be the integral when we fix x and then integrate with respect to y. So this area of this slice is an integral from c to d. Y goes from c to d of f of xy dy. And so if we do the integral where we integrate with respect to y first, we get the area of these slices, and then we add up the areas of all those slices in order to get the volume, gives the double integral. Okay. So this is the way we can evaluate double integrals, is by splitting them up into these two iterated integrals, the inner integral and then the outer integral. One point to add is that sometimes it's easier to do the integral one way or the other. So in fact, you may be trying to do a specific double integral. One of the two orders, integrating with respect to x first or y first, may be much easier than the other. In fact, one of them may be not possible to do in terms of elementary functions, but then you switch it to the other way and you're then able to evaluate the double integral. So if you're trying to do one of these, you may want to try it in both ways. All right, I'm going to do now a few examples of evaluating double integrals using this technique I've been describing, iterated integrals. And so the first integral we'll look at is this integral of f, which is x squared minus y squared over this given rectangle. So let's draw the situation here. We want to integrate, do a double integral over the rectangle R of x squared minus y squared dA, and the rectangle R, described there in the statement of the problem, but I'm going to draw the rectangle R in the xy plane. So now we're looking down along the z-axis into the page and looking at the xy plane. So this is the x-axis and the y-axis. And this rectangle, let's see, x goes from 1 to 3 and y goes from 0 to 2. This rectangle here, R, and so we're calculating the volume of a region above this rectangle R and below this graph. And actually, one thing I didn't mention is that, as in the one-dimensional case, if the volume goes, or the graph goes underneath the xy plane, then we count the volume as negative. And so this function is negative in any part of R, then the part of the volume which is underneath the xy plane is counted as negative, just as in the one-dimensional. Okay, so let's evaluate this by converting it to an iterated integral. And I'm going to do it both the possible ways, integrating with respect to x first and with respect to y first. X goes from 1 to 3 and y goes from 0 to 2. So let's first do the iterated integral, integrating with respect to x first. So where the x integral is the inner integral. So I think the clearest way to do these is to first draw out all of the integrals without the limits, and then add in the limits. Sometimes it can get confusing what limits you're supposed to put, which one should be the x limits and the y limits. So write out the iterated integral like this without the limits, and then we'll put in the limits in the two integrals. So x, the inner integral, x goes from 1 to 3. And here is 1 to 3. Y, the outer integral, goes from 0 to 2. Okay, and so now we're going to evaluate these integrals. So at this point, it's a matter of evaluating one-dimensional integrals using the fundamental theorem of calculus, which we've done before. But maybe it gets a bit confusing since it's in a different context. So I'll go through all the details here. So we first of all have the same integral with respect to y, and we want to find the indefinite integral of the integrand x squared minus y squared with respect to x. We treat y as being a constant. Y is held constant, so we're finding the area of this slice. And so when we find the indefinite integral of x squared minus y squared with respect to x cubed over 3 minus y squared times x, and the limits here from 1 to 3, and we still have this dy to indicate that the outer integral is with respect to y. And if it's there's potential for confusing the limits x and y here, so maybe we want to say that these limits are with respect to x, from x equals 1 to x equals 3. Okay, and so let's plug in the 3 and 0 for x. So when we plug in 3, we get 3 cubed is 27 divided by 3 minus y squared times 3, so 3y squared. That's the x equal 3 limit. And then let's put in the x equal 1 limit, minus 1/3 plus y squared. All right, so now it's simple, a really pretty simple integral with respect to y. We're going to want to combine all the terms together. Integral from 0 to 2. So we have here 26/3 minus 2y squared. And combine the terms. And then, well, this is an integral, I hope, for you. 26 over 3y minus 2/3 y cubed. Evaluate from 0 to 2. And so let's see, we have, we'll put in 2 for y, we get 52/3 minus 16/3 is going to be 36/3 or 12. So this double integral that we wanted to calculate is 12. That is the volume in between the xy axis and the graph of this function. Possibly counted as negative if it goes below the xy axis. All right, let's try to do the same problem now, where we integrate with respect to y first. So we do the inner integral, integrating with respect to y. So, start again, the double integral. And the region R is shown here. Need to write the double integral again, but there we are. So there's the region R for reference. Integral. I'm going to write the integrals first without the limits and then fill in what the limits are like I did last time. And this time the inner integral will be integration with respect to y. The outer integral will be integration with respect to x. And so for the inner integral with respect to y, y goes from 0 to 2. The outer integral with respect to x, x goes from 1 to 3. All right, and now we follow the same procedure, just doing one-dimensional integrals as we did before. Integral from 1 to 3 find the indefinite integral now with respect to y, where x is held constant. So that's going to be x squared y minus y cubed over 3, evaluated from y equals 0 to y 2 x. And now let's plug in the limit. So the y equals 0 doesn't contribute anything. We just have the y equals 2. So this is the integral from 1 to 3 of 2x squared minus 8/3. And now let's do the integral with respect to x. So finding the indefinite integral, we get 2/3 x cubed minus 8/3 x, evaluated 1 to 3. Right, and so let's plug in the x equal 3 and x equal 1. So 3 cubed is 27 times 2 is 54. So you have 54 thirds minus 3 times 8 is 24 thirds minus 1 2/3 plus 8/3. All right, so let's see, we get 30 thirds minus 2 is 28 thirds plus 8 is 36 thirds, which is again 12. Okay, so we got the same answer doing the integration with respect to y first as the inner integral. Okay, I'm going to do another example. I'm going to integrate the function which is simply constant over the same rectangle as in the previous exercise. And so in one dimension, when we integrate a constant, you just get the area underneath the constant graph in between the two endpoints of the integration, and so you get the length of the interval you're integrating over times the constant. And it's the same here. So when we do this double integral of a function which is equal to 1, we just get the area of the rectangle at the base times the height of this cuboid that we're finding the volume of. So let me draw going on. So again, drawn is three-dimensional axes. And so this is the x-axis, y-axis, and z-axis. And x in the rectangle that we had in the previous exercise went from 1 to 3. Goes from 1 to 3. Y went from 0 to 2. So the rectangle R that we integrate over is 1. And then the function we integrate is f equals 1. So here's 1. And so this is just a cuboid that we're finding the volume of. The cuboid with height 1 and area at the base of 2 times 2, which is 4. So this double integral over the rectangle R of the constant 1 is equal to 1, that's the height, times the area of the rectangle R. This is simply because it's the volume of a cuboid, the height times the width times the length, if you like. This is 1 times 2 times 2, so 4. 4 is the volume of this cuboid, and that's the double integral. So in this case, we can just say what the double integral is, just because we know that it gives the volume of this region below the graph and above the xy plane. Okay, I'm going to look at one more example of doing a double integral, somewhat similar to the previous two. And we're going to integrate this function x cosine y over the given rectangle. Back in so we can refer to it. Okay, so now the double integral for this rectangle of x cosine y Okay. And so let me draw the rectangle. XY plane. Here's the x and y axes. So we have that x goes from 0 to 2, in this case, and y goes from 0 to pi over 2. Pi over 2 is around 1 point. Let's just say it's here. Region R is this region. Okay. 2. Right, so I won't go through the entire process of evaluating this in both ways, either doing the integral with respect to x or y. We'll just do one of them to calculate it. So let's do integration with respect to x first as the inner integral, and then with respect to y second. So once again, I'll draw the integrals. I'll do the inner integral with respect to x, outer integral with respect to y. And now I'll put in the limits. So x goes from 0 to 2, and y goes from 0 to pi over 2. Okay, so I'll do this integral with respect to x first. Find the indefinite integral, x squared over 2. Y is simply held constant, so cosine y, same. Integral from 0 to 2, so this is from x equals 0 to x equal 2 dy. Okay. So then we put in x equal 2 and x equal 0. When you put in x equal 2, you just get 2 here. So integral from 0 to pi over 2 of 2 cosine of y. And of course, the antiderivative of cosine is sine. So 2 sine y, and some of you may have noticed I forgot to write pi over 2 here, so let's put that back in. So 2 sine of y, evaluated from 0 to pi over 2. And when you plug in y equals 0, you get 0. When you plug in pi over 2, you get 1. So this is 2. Double integral. Okay, so that's it for the first lecture. In the next lecture, or the next video, we're going to look at some applications of double integrals. So finding the mass of a plate with varying density, and also something called the moment of inertia.